The valence shell electron pair repulsion theory, abbreviated VSEPR, starts from the general principle that valence shell electrons occupy essentially localized orbitals. Mutual interaction among the electrons orients the orbital in space to an equilibrium position where repulsion becomes minimum. The stereochemistry of the central atom in a molecule is then determined by the repulsive interactions among all the electron pairs, bond pairs, and lone pairs in its valence shell. A lone pair is concentrated around the central atom, while a bond pair is pulled out between the two bonded atoms. As such, repulsion becomes greater when a lone pair is involved. The rule is illustrated by the gradual change in bond angles. In CH4 it is 109.5 degree, whereas in ammonia it is 107.3 degree, and H2 where two lone pairs are present in oxygen is 104.5 degree. CH4 contains no lone pair of electrons. The bond pair interactions bring about the most stable equilibrium bond angle of 109.5 degree, the angle predicted from sp3 hybridization. NH3 contains one lone pair and H2O 2. Repulsions tend to reduce the bond angles. The lone pair and lone pair repulsions tend to reduce the bond angles. The bond pair interactions tending to open the bond angles are weaker, and hence the ultimate angles are smaller than 109 degree 28 minute and still smaller in H2O where two lone pair atoms are present. The bond pair is pulled between the two bonded atoms and its charge cloud is thinned. As the bonded atom becomes more electronegative, the charge cloud is displaced further away from the central atom and repulsion decreases. The following bond angles may be compared. Ammonia is 107.3 degree, whereas in NH3 it is 102 degree. The VSEPR rule also explains the positions of lone pair in trigonal bipyramid or octahedral arrangements in ClF3 or I3 minus or ICl4 minus or SF4 or BRF3. In the trigonal bipyramid structure, a group in the equatorial position has two nearest neighbors at 90 degree above and below the equatorial plane. On the other hand, the two equatorial neighbors to this group are situated at an angle of 120 degree. Repulsion between the bond pair or lone pair of electrons decreases greatly as their angular separation increases. As such, the equatorial group will experience too strong repulsion from the axial neighbors at 90 degree and too weak repulsion from the equatorial neighbors. If we consider the environment of any group in an axial position, we find that it has three neighbors at 90 degree in the equatorial plane. Consequently, it will experience three strong repulsions from its neighbors. The principle of minimum repulsion will now suggest why lone pairs will be preferably placed at equatorial positions, because where it is facing two strong repulsions rather than axial positions where involving three strong repulsions. For the same reason, lone pair in octahedral arrangements occupy trans positions rather than cis positions.